Malaysia energy demand will face challenges as the country depends mostly on the natural gas and coal for electricity. In 2019, the amount of electricity consumed in Malaysia totaled just below 150 billion kilowatt, an increase from the previous year. Engineers in Malaysia is always in need for research and development on developing technologies on power generation in this country. Our team was assigned by the Malaysian government to design a combined power plant. These are the specifications of the combined power plant. We will be designing the combined power plant based on basic concepts in thermodynamics. Those two concepts are the Rankine cycles and Brayton cycle.
From the schematic diagram, firstly, at stream number 1, the air feed at ambient temperature and pressure will be pressurized and sent to the combustor. The combustor then will heat up the stream to 1800 Kelvin. Then, the stream will go to the gas turbines through a splitter which will halve the flow rate. After entering the gas turbines, the energy will be used and the temperature and pressure will drop to 1151.97 Kelvin and 100 kilopascal. The stream then will move to the heat exchanger 1 through a mixer which will combine back both streams. Then, the stream will exchange heat with the steam cycle and goes out as air stack at 1181.30 Kelvin. Moving on to the steam cycle, firstly, the saturated liquid at stream number 9 will be pressurized to a compressed liquid at stream number 6. The stream then will exchange heat with the steam from the gas cycle and heated up to 700 degrees Celsius at superheated vapor state at stream number 7. After that, the stream will be transported to the steam turbines through a splitter. After entering the steam turbines, the energy will be used and the stream at liquid vapor mixture state will be sent to the condenser or the heat exchanger 2 through a mixer at stream number 8. After exchanging heat with the surrounding air and cool down, the stream will then be recycled back into the pump as saturated liquid. Here are the schematic diagram by using the block and diagram in HYSYS.
I'm Eunice and I'll be explaining the calculation part. Before conducting the calculation, few assumptions has been made. First, it is steady operating condition. All process occur in quasi-equilibrium process and there's no leakage on the pipeline. First, we assume one gas turbine with 72 efficiency can produce 386 MW. There is no heat transfer from energy balance equation. By having two gas turbines, the work out calculated is approximately 772 MW. We proceed to the gas compressor with 80% efficiency. Since there is no heat transfer from energy balance equation, the work in will be 368 MW. Proceed to combustor, heat absorbed to heat out the stream is 197 MW. Heat exchanger, since heat absorbed by the water is equal to heat lost by the air, by manipulating the energy balance equation, we can obtain the outlet temperature of the air. Total work out of the gas cycle will be work out of turbine minus work in of compressor, which is 407.23 MW. Assume a steam turbine can produce 50 MW and having isentropic efficiency of 96%. Next, for condenser, since tube is chosen as control volume, we can calculate the heat transfer out by water and heat absorbed by cooling air. Saturated liquid enter the pump with isentropic efficiency of 80%. Since there is no heat transfer and work generated, the actual work in of pump will be 3218.32 kW. The compressed liquid fall to the heat exchanger and heat up to superheated vapor by 25,372.11 kJ per second. Total work out of steam cycle is work out of steam turbine minus work in of pump, which is 92.78 MW. Therefore, the actual power produced will be the sum of work from gas and steam cycle, which is 500.01 MW. The amount of steam generated is calculated from the superheated stream, which is 3,958.8 m3 per hour. contrasted with heating value of 30,800 kJ per second is used. Amount of coal needed can be calculated by dividing heat energy transfer in with the heating value. Therefore, 566,1792 kg of coal is needed per day. Proposed power plant: 2 steam turbine, 2 gas turbine, 1 pump, 4 generator and 1 combustor is needed. The overall efficiency can be calculated as total work output divided with the heat transfer in. Therefore, overall efficiency will be 0.2537 and the back work ratio will be the total work in divided by the total work out, which is 0.424.
Let's move to the discussion. For on our reading on journal regarding the gas-fired power plant is shown in the schematic diagram above. Our proposed solution is similar to the schematic diagram above, but we have made some modification to it in order to produce more power from one cycle and increase the efficiency of the component. To achieve our goals, we have run it using icon simulation and trying with different methods and values in order to maximize the performance of the power plant. At the same time, we also consider the emission of harmful gases by implementing carbon capture facilities so that the construction of the power plant will not lead to severe environmental pollution and increase the feasibility of the project. In this project, we focus to the gas steam power plant. In this combined gas steam power plant, there are 2 types of cycle model. The first cycle is Brayton cycle. Gas turbine usually operate on an open cycle. Fresh air at ambient condition is drawn into the compressor, where its temperature and pressure are raised. The high pressure air proceeds into the combustion chamber where the fuel is burned at the constant pressure. The resulting high pressure gases then enter the turbine, where they expand to the atmospheric pressure while producing power. The second cycle is Rankine cycle. Rankine cycle is the ideal cycle for vapor power plant. The ideal Rankine cycle does not involve any internal irreversibility and consists of following process. The process is isentropic process, constant pressure heat addition in a boiler, isentropic expansion in a turbine, constant pressure heat rejection in a condenser.